process P1 is done execution, it is out of the picture because it is finished. Hello everyone, I hope you're doing fine. Today we'll be discussing operating system deadlocks. So let's get right to it. So the deadlocks are something which arise in operating system when we have a scenario when we have multiple processes and multiple resources. So we must know what the system model is if we are trying to understand the deadlock scenario. So we have multiple processes and we have multiple resources like R1, R2 up to Rm, and these resources could be CPU cycles or memory space or IO devices. So you must be getting an idea that a process may be interested in any of these resources multiple times during its life cycle. So whenever a process requests for a resource of this type, it must do certain things, like it should request because it is it needs the resource. So what would the process do? It will first of all request the resource from the operating system. So every process must request the resource from the operating system. Then naturally the process uses that resource, and when it is done using that resource, it releases that resource, right? So this will be our system model, and these are certain you can say conditions. When these conditions are present, the deadlock can happen. The first one is mutual exclusion. Every operating system normally has this, that once a process acquires a resource, and as we saw in the chapter of process synchronization, we saw a critical section. So every process uses a resource in its critical section, right? So I may have mentioned that a resource is basically something which is being like a shared memory segment is being accessed by the process inside the critical section. So every operating system uses mutual exclusion on the resources to make them mutually exclusive for a process, right? Only one process is allowed to access the resource at any given time. The second condition for deadlock is that whenever a process is holding a resource and it is requesting another resource or waiting on another resource, then we can say that the process there can be a deadlock. Similarly, the third condition for deadlock is that we cannot preempt a resource from the process. In other words, we cannot take away or take back the resource the operating system gave to the process. We cannot do it per force. So the operating system must wait for the process to release the resource. This is the third condition for deadlock. The fourth condition for deadlock is circular wait, and circular wait is something which can be explained in such a way that, for example, we have so let me explain this with an example here. We have, for example, we have process 1, we have a resource called resource 1, we have a process called process 2, and we have another resource called R2. These are all the processes and resources which exist in the system. So there comes a point in the life of these processes P1 and P2 that P1 has acquired resource R1. It requested resource R1 from the operating system. The operating system gave that resource to process P1. Process P1 now has the control of resource R1, and similarly at the same time process P2 requested resource R2 from the operating system, and R2 was given to process P2 by the operating system. This is these two things happened in parallel or one after the other, but before the things which are going to happen now. The third thing that happened was that process P1 became interested in R2 while holding R1, and the fourth thing that happened was that process P2 became interested in R1 while holding R2, right? So this is a circular wait. This is a circle kind of thing. So process P1 is requesting R2, which is held by P2, which is being requested by which is requesting R1, which is held by P1, which is again requesting R2. So in this circular fashion there's a circular wait, and this is the fourth condition for deadlocks. So resource allocation graphs can be used to represent a deadlock scenario, and just as I drew them earlier, processes are drawn like this, resources are drawn like a square, and if there are smaller squares inside a bigger square, it means that that resource has multiple instances. Like for example, USB port is a resource, and if you have 4 USB ports in your computer, it means you have 4 instances of the same resource type, which is USB port. This is a scenario where you can see that process P1, so if an arrow goes from a resource to the process, it means that that process is holding that resource, right? And if an arrow is going from a process to a resource, it means that process is interested in that resource. It is looking towards that resource to be given to it. In other words, it has requested that resource. So for example, in this scenario, you can see you may be tricked by this, that there's a circular wait going on between P1 and P2, but the thing is that process P3, which is holding R3, will eventually release this R3, because P3 is not looking forward to get or to acquire another resource. No, it is not happening, right? So eventually, no matter how much time it takes, process P3 is going to eventually release R3. R3 is going to be then given to will be given to P2, and then P2 will have all it needs, because P2 already have R1, P2 already has one instance of R2. P2 is looking towards R3, but R3 was given to P2 eventually after P3 was done with it. So now P2 can go on with its execution, and eventually when P2, no matter after how much time is done with its execution, will release R3, R1 and this instance of R2. So when this happens, R1's this single instance of R1 is given to P1, and then P1 finishes execution, and because P1 was only waiting for R1. So this is an example of a resource allocation graph where there is no deadlock. This is an example where there is a deadlock, because you can see that process P1 is waiting on R1, which is held by P2, which is waiting for R3, which is held by P3, which is waiting for a free instance of R2, but both of these are being held by two. So if we go through this direction, to this branch, we end up in the circular loop. If we go through this branch, we again end up at this part. So there is one cycle becoming here, and there is one cycle becoming here. So this this particular resource allocation graph has 2 cycles, right? And there is a deadlock. Similarly, there can be other examples of graph where there is no deadlock. So mainly there are 2 methods of handling a deadlock. The first one is deadlock prevention, and the second one is deadlock avoidance. Let's look at deadlock prevention first. Deadlock prevention simply takes the idea that if we are able to prevent one of the 4 conditions of a deadlock to happen, which we looked at earlier here. So if we are able to prevent any of these 4 conditions, we will actually make it impossible for a deadlock to happen, because one of the necessary conditions for a deadlock to happen cannot happen now, right? Because we intentionally made it impossible by preventing one of these conditions. So that is really difficult to do, because in order to do that, we'll have to declare resources shareable, but it's not always possible to have all the resources shareable by multiple processes at the same time. Or we can implement a condition that if a process is holding a resource, it cannot request another resource. Again, this is not a very practical condition. Similarly, we say that whenever deadlock is feared, we simply take away the resource from a process to prevent a deadlock. Again, this is not always feasible. We cannot forcefully take a resource back from a process, or we prevent a circular wait kind of thing, and we have an algorithm running inside the operating system which looks for a circular wait kind of situation, and as soon as it is about to happen, the operating system tries to prevent that circular wait. Again, this is a difficult thing to achieve, but there is another method of doing this. Instead of prevention, we have deadlock avoidance, and deadlock avoidance runs an algorithm to see whether a new request made by a process for a resource will or can result as a deadlock. So if it sees that thing happening, that request is not granted, right? So the deadlock avoidance runs in such a way, and to do that, the deadlock avoidance algorithm makes use of an algorithm, and that algorithm looks for a safe state. So if the operating system finds the processes and resources in a safe state, the operating system says that that scenario is not leading to a deadlock, so we can grant the request of that process. So let's look at what a safe state is, and this is I'm going to explain this using an example. So for example, we have 12 resources of same type, right? We have 3 processes. So for example, we have any kind of 12 resources, and all the 3 processes. For example, one process is called P0, second one is called P1, third one is called P2. They can be interested in multiple instances of this resource, which is of one type, but there are 12 resources available. So we want to see that can there be a situation when there can be a deadlock between these three processes, P0, P1 and P2, and which will mean that they will cease to execute further. So if there is a deadlock, they will cease to execute further. So we want to prevent that situation, and one of the constraints of this algorithm is that before execution or during compilation, maybe the process declares how many resources it is going to request from the operating system during its life cycle. So process P0 has declared that during its life cycle the maximum number of resources it can ever request is 10. Similarly, the maximum number of resources process P1 is declaring it can ever request is 4, and process P2 is declaring that it is going to request at most 9 resources. Currently each process is allocated some instances, right? So for example, P0 is allocated 5 instances, P1 is allocated 2 instances, and P1 is allocated 2 instances, and P2 is allocated 2 instances. So we want to check whether the state is safe. In other words, if we give all of the maximum need to any of the process, can the process finish its execution? So we make another column which is called need column. So if this is the maximum and this is the current allocation, what can be the maximum need of this process? The maximum need can be 10 minus 5, which is 5. Similarly, process P1 can at most request 2 more instances of this resource, because 4 minus 2 is 2. Similarly, process P2 can request 9 minus 2, 7 more resources. So this is the need of each process. So how many resources right now are available? So we're going to add up all of these, and we get 5 plus 2 is 7 plus 2 is 9. So currently we have 9 resources which are allocated to the processes, while the total number of processes are 12, right? So can we meet the need of any of the resources? Can you see that? So yes, you can see that we can meet the need of process P1 because it only needs 2 resources. So if in this list there was none of the process, there was no process which was whose need we could meet using the currently available total instances, which is 3, so we would say there's a deadlock. So we can say that okay, I can meet the need of process P1. It is going to execute, it is going to release its current allocation. So P1 executes and it releases all the resources it was holding, and which were 2. So now the previously 3 were available, so now 2 become available. 3 plus 2 equal to 5 become available to the operating system. So now out of these, so we can say process P1 is done execution, it is out of the picture because it is finished execution. Which is the second process we can meet the need of if we have 5 overall 5 total available instances? We can meet the need of process P0. Again, even at this stage, if it was impossible to meet the, for example here it was 8, so we won't be able to meet the need of this or this using 5, right? So then we'd say that this system is not in a safe state. But right now, because this is 5 and we can meet the need of process P0, we say the system is so far in a safe state. So what we do, we allocate this 5 to that, and the process P0 finishes execution, gives back its 5. So when it gives that back its 5, this 5 becomes 10. So P0 finishes execution and gives back its 5. So now we have 10 free resources. Can we meet the need of this third process P2? Yes, we are able to do that. So then P2 executes and gives back its allocation, which was 2. So 10 plus 2 equals 12. So now we, because all of the processes are finished executing, so we get back the total number of resources which was originally available, which is 12. So this is called the safe state algorithm, and this is how we are able to check for whether the deadlock can occur or not. So this was the example for safe state, and when a system is in safe state, there is no chance of deadlock happening. But if the system is in unsafe state, meaning that if the request that is being made by a process takes the system in an unsafe state, then there is a possibility of deadlock. So we want to we won't meet the request of that process, and we will bring back the system into safe state, right? So then there's an algorithm called the banker's algorithm. So if we have multiple resources, we have multiple processes, and each process can have each resource can have multiple instances, then we will have to employ banker's algorithm, because the previous example that we saw only used one resource type. So if we have multiple resource types, then we will have to employ banker's algorithm. Banker's algorithm makes use of different data structures, like the banker's algorithm makes use of multiple data structures, like for example there's an available array, a vector of length m, where m is the number of resource types, right? Similarly, there is a matrix of size n cross m, which is called max, and n represents the number of processes, m represents the number of resource types. There is a matrix called allocation with the same dimensions. There is a matrix called need with the same dimensions, and all of these things, as the name suggests, available represents the number of available resources, max represents for each process number of resource instances which are at most will going to be requested by the process. Allocation means current allocation of the process of that resource, and need is the need of that process for those resources. Okay, so these data structures are available to us, and this is the safety algorithm of the banker's algorithm, which iteratively checks for all, allocates the resources to the processes, and iteratively checks whether all of the needs can be met. So I'm going to show all of this algorithm using a numerical example. So this is a numerical example, so let's see how it is solved. For example, we have a number of processes like P0, P1, P2, P3 and P4. We have a number of resources like A, B and C. Each resource can have multiple instances. They have multiple instances. A has a maximum number of instances of 10. B has a maximum number of instances of 5, and C has a maximum number of instances of 7. So these are the number of instances that each of these resource type have in existence. So there's an allocation matrix which shows, for example, in the first row, how many instances of type A does process P0 right now is allocated, right? So P0 is allocated 0 resource instances of type resource A. P0 is allocated 1 instance of resource type B. P0 is allocated 0 instance of type C. P1 is allocated 2 instances of type resource type A. P1 is allocated 0 instance of type B, and this goes on like this. And let me fill out the rest of the table and then we can move forward. Similarly, we have a max table which was declared by all of these processes before execution. So this is a separate matrix, and again we have these 3 types of resources. So process P0 wanted a maximum of 7 resources of type A. Similarly, process P0 wanted 5 resources of type B, and similarly process P0 wanted at a maximum of 3 resources of type C. Similarly, process P1 wanted a maximum of 3 resources of type A, and so on. So let me fill out the rest of the matrix and then we'll proceed. Right? So based on these 2 matrices, we construct a matrix of our own which is called the need matrix. So obviously need matrix will have for each process and resource a number which is, a difference of maximum and the allocation. So for example, process P0 has 7 maximum requirement of type A process resources, while currently it is allocated 0. So how much its maximum need is? 7 minus 0. So we do that for all of these pair of max and allocation, and we calculate the need. So 7 minus 0 is 7, and again these are A, B, C, 3 types of resources, and again 5 minus 1 would be 4, 3 minus 0 would be 3. So we repeat this for all of the matrix. 3 minus 2 would be 1, 2 minus 0 would be 2, 2 minus 0 2, 9 minus 3 6, 0 minus 0 0, 2 minus 2 0, 2 minus 2 0, 2 minus 1 is 1, 2 minus 1 is 1, 4 minus 0 is 4, 3 minus 0 is 3, 3 minus 2 is 1. So now this matrix shows all of the need of all the processes for all the resources, right? So now what do? Now we have to find out whether the system is in a safe state. In other words, are we able to meet the needs of each of the process one by one? Ideally at the same time, but even if we're able to meet the needs of all the processes one by one, it will be fine. It is fine with us. So first we need to calculate how much out of this total is the resource set available to us. So let's calculate that. We add all of the allocation for type A resource, right? So all of the type A resources being allocated to all the processes, the sum will show how much of resource A is given to the processes at this particular time. So 2 plus 3 is 5, 5 plus 2 is 7, so the answer would be 7. Similarly, 1 plus 0 plus 0 plus 1 plus 0 is 2, so that means 2 is the number of resources of type B which are currently given to all the processes. Similarly, 0 plus 0 plus 2 plus 1 plus 2 is 5. So the current allocation of type A and B and C, the total allocation is 7 to 5, while the total existing size is 10, 5, 7. So what do? We subtract this. So 10, 5, 7 minus 7 to 5. This will be the availability of resources to us right now. 10 minus 7 is 3, 5 minus 2 is 3, 7 minus 5 is 2. So 3, 3, 2, and let me write it over here. 3, 3, 2. 3, 3, 2 is the current availability of resources. So now you look at the need column, need matrix, and try to find out a process whose need we are able to meet using this 332. Which one it is? Can we meet the need of 743? It requires 7 and we have 3, so no, we cannot do that. It cannot be done, right? So this is out of the same. 122. It requires 1, so we are able to meet using 3. It requires 2, we have 3. It requires 2, we have 2. So that means we are able to meet the need of process P1, right? But we are not able to meet the need of other processes. Maybe one of them, like for example, we may be able to meet the need of P3, but we simply take the first process, which is P1, right? Let's just make a list of processes which are able to run. P1 is able to run. How much resources was P1 holding? P1 was holding 0, 1, 0. So if we are able to meet the need of P1 and P1 takes something from us and finishes execution, it gives back all the resources it was holding. So let's assume that it did that and it gave us back 0, 1, 0. So 0, 1, 0 is going to be added to the currently available number of resources. So the new number of resources become 3 plus 0 is 3, 3 plus 1 is 4, 2 plus 0 is 2. So now we've got 3, 4, 2. So we look into this matrix and we see which process can we meet the need of, and if we find that, we assume that that process can run and we simply check it out of the list and we keep on doing that. If we are able to find a safe sequence, a sequence for which we are able to meet the needs of all the processes in sequential order, we say that the system is in a safe state, right? So I encourage you to try it out on your own and finish this sequence and see whether all the needs are met, or there is a point where we are stuck, and with there is a point where we cannot meet the need of any remaining processes. So this is from my side from Deadlocks. So I just wanted to keep it brief from Deadlocks, because I just want to keep you focused at the main part. So we have covered the main part, so let's go to the next one in the next video. So I hope you like the video. See you next time.